So I solve for m dot 2 is equal to 0.4938 kilograms per second. And m dot 1 is equal to 0.0617 kilograms per second. In what we were asked as well, so this gives us the mass flow rates. What we were asked as well was to find the diameter of the pipe given a certain velocity. So we're given a certain velocity, and we're given that the V1 was 70 meters per second, and we wanted to find the diameter one. So we wanted to find that. And now what we're going to do is we're going to do the mass flow rate is the area times the velocity divided by the specific volume. So we know what these various values are. So m dot 1, we have all these values, so we can substitute in and we can solve for A1. So A1 is equal to 0.0617 times the specific volume 2842 divided by the velocity 7. So A1 is equal to 0.12302.505, and this is equal to pi over 4 d1 squared. So d1 is equal to 0.0178 meters. So it's equal to 1.78 centimeters. So in this problem, we found the mass flow rates. Finding the mass flow rates enable us to size pipes. So if I know what the velocity is, and you're given it in this case, but if you know that by regulations you don't want to have too high a velocity, then this determines your velocity. Knowing your mass flow rate determines your pipe size. And now what we want to do is introduce two other pure substances, R12, refrigerant 12, and ammonia. And these two substances are used as refrigerants, and there are tables of properties for them. And so table A9 and A10 are for ammonia, and A11 and A12 are for R12. Now R12 is a refrigerant that's no longer used, but it's the one I have tables for, and I might as well digress just slightly with R12. It's dichloro-difluoromethane. So methane is CH4, and so if I take CH4, here's the C, and I strip off the hydrogen and I replace them with chlorine and fluorine, I have dichloro-difluoromethane. And that's the refrigerant, and all the refrigerants that are used are some type of fluorinated hydrocarbon. And so what happened with this is that when in the ozone layer, so ozone is very active oxygen, so sunlight going in would knock off a fluorine and chlorine. They're very active chemicals that act with the ozone and deplete the ozone layer. So then you'd have more ultraviolet rays coming into Earth. So that's why R12 was banned in terms of its use. It was a good refrigerant. It was banned in the United States. It's still used in other parts of the world. So with these tables, so if I look at the tables, so if you go and look at them, you'll see there's no internal energy. There's no internal energy there, so you have to use the definition of enthalpy. H is equal to U plus PV, and solve for U. So U is equal to H minus PV. So what if I need internal energy, if I need it, I have to calculate it this way. So let's do an example for that. So let's say with R12, we're going to find U for saturated vapor at minus 10 degrees C. And notice that for R12, there's only one saturated table. So whereas for steam we had A5 and A6, here there's only one, and it has temperature being evenly incremented. And so in this case, it would be table A12, A11 rather. And we're going to look up these values. You'll notice that P is in MPa. So you have to multiply by 1,000 to get kPa. So at minus 10 degrees C, we have P is equal to 0.219 MPa, which is equal to 219.1 kPa. We have H sub G is equal to 183.058, and we have that V sub G is equal to 0.076646. So basically, we're going to substitute in the equation that we just did for internal energy. So U sub G is equal to 183.058 minus the pressure, 219.1, times the specific volume, 0.076646, and we find that U sub G is equal to 166.26 kilojoules per kilogram. And if we look at the superheat tables for R12, that it's arranged in the same way that the steam tables are, so that the superheat tables are arranged the same way. So if I look at in A12, so if I look in A12 at 200 kPa, which is 0.2 MPa, and I look at T is equal to 30 degrees C, I can find that H is equal to 208.446 kilojoules per kilogram. So you use the superheat tables the same way we did with steam for superheat tables. Let's examine the difference between H sub Fg at 30 degrees between ammonia and R12. You'll just see why ammonia is a very popular refrigerant. It's still used today. I obviously don't want to breathe it, but it has very nice properties, thermodynamically speaking. So let's look at H sub Fg at minus 30 degrees C, and for ammonia, it's equal to 1360 kilojoules per kilogram. And for R12, it's equal to 165.2 kilojoules per kilogram. So we notice that the ammonia has a much greater heat capacity per unit mass as it moves from liquid to vapor. And you'll notice for ammonia as well that the superheat tables are arranged in rows and not columns. For NH3, superheat, the pressure is in rows. And so, for example, if I go in at P equals 125 kPa, so if I go in at that pressure in a temperature of 10 degrees C, so the temperature goes across the top. So when you look at the superheat table, you'll see it goes across the top. I find that the enthalpy is equal to 1493.9. So I can just look that up and find out what those values are. And now, let's look at another problem. So now let's look at a more complicated problem, problem 4.6. So in problem 4.6, and I urge you to look at the text before looking at what goes next and read the problem and make sure that you can translate what's being said in words into a sketch and see what you have to be doing. I know how to translate it. I also wrote the problem, so it's a different issue for me. So in this case, we have a tank. It has R12 in it. I know the diameter of the tank is 20 centimeters. It's 120 centimeters high. It's R12 at 20 degrees C. The weight is 370 newtons. And we want to find the mass of vapor or the mass of liquid. And we also want to see where this liquid line is. So we're curious as to how much of this is filled with liquid and how much is not. And so with this, there are a couple of things. This isn't the quality because this is just the ratio of the vapor to the mass, so a different thing. And this is the weight, and so that isn't mass, that's force. So now we have to find the mass. So the mass is equal to the weight, 370, divided by 9.8, is equal to 37.75 kilograms. I'm going to calculate the volume so I can find the specific volume. And so the volume is equal to pi over 4 d squared L. We're going to do it in meters. Pi over 4 times 0.2 squared times 1.2. And it gives us a volume of 0.0377 cubic meters. And the specific volume is equal to volume over mass. So the volume is 0.0377 divided by 37.75. And this turns out to be 0.001 cubic meters per kilogram. Isn't that a nice number? Isn't that so fortuitous? So now what we can find that since I know the specific volume, I can find the quality and I can find out the amount of vapor and the amount of liquid. So we're going to find the quality. So V is equal to V sub F plus X V sub Fg. And so I have here V I know 0.001. V sub F is 0.1230752 plus X times V sub Fg 0.03003. And I get that X is equal to 0.0082. And this is the mass of vapor over the mass of vapor plus mass liquid. So what I want to do is find the mass of the vapor, the mass of the liquid, and then I can get the ratio that we need. So the mass of the vapor is equal to X 0.0082 times 37.75. So I have that the mass of the vapor is equal to 0.317 kilograms, and the mass of the liquid is 37.75 minus the mass of the vapor, so that's equal to 37.44. kilograms. And so the ratio of mass vapor to mass liquid is 0.3177 divided by 37.44, and that's equal to 0.20832. And now what I want to do, so now that I know the mass of liquid, so I know what the mass of liquid is, I know its specific volume, so its specific volume is V sub F. So for the mass of liquid, V sub F, I already know. I know what that is. It's that 0.00 thing. So now I can find the volume of the liquid. So this enables me to find the volume of the liquid. So with this, I can find the volume of the liquid. So it's the mass of the liquid times the specific volume. So I have 37.74 0.44 rather, times 0.123752. And so I have that the volume of the liquid is equal to 0.02815 cubic meters. And I know that the volume is also pi over 4 d squared L. I know the diameter, and L is going to be how far up from the bottom the liquid is. So if I substitute in here, so I have pi over 4, d squared is 0.2 squared times L, and it's equal to V sub L. And I solve, and I have that L is equal to 0.896 meters, or 89.6 centimeters. So when I looked at the tank, it's 120 centimeters, and the liquid line is up here at 89.6. So that tells me what the liquid line is. So you have a little practice doing some of these problems too. For homework, do 4.8, 4.16, 4.31, 4.43. So what we want to look at next is a throttling calorimeter. And this is figure 410 in the text, page 115. Now the drawing in the text is much better than I can draw, so you may want to look at that while we look at this. So what we want to do is to be able to measure steam quality. And so one of the ways they do it is with a laser, and they shine a laser through the steam, and you look at the dispersion of the beam, and the greater the dispersion caused by the droplets, they can then link that to the quality. So it's the dispersion of beam by droplets. And another way is with the throttling calorimeter. And here, it's typically X is greater than or equal to 95%. So what happens is that this works, but only under these circumstances. It doesn't work for very wet steam. And I'm going to need a certain pressure drop to make this happen. So if I draw the sketch that's in figure 410. I'm going to have a pipe in here. It's going to have slots in it. And it's going to go through a valve. And it comes out. And I'm going to measure temperature. And I can measure pressure. And so this typically goes out to P atmosphere. And so I have state 1 and state 2. And the idea behind this is that we're going to have a pressure drop so that we move this is a throttling process, and we move this into the superheat region. So if I look at this first law, I have Q dot plus M dot H1 is equal to W dot plus M dot H2. It's adiabatic, there's no heat loss, there's no work done, and so I have that H2 is equal to H1. If H2 is superheated, then I can, using H1 is equal to H2 is equal to H sub F plus X1 H sub FG. So that's the strategy behind it. That was the superheat region. Knowing temperature and pressure, I can find the state, and then I back calculate to get the quality at the initial state. In a TV diagram that looks at this, or shows what's going on, is that I'm at an initial pressure here. So here I have P1, I'm here it's state 1, and you're hoping to go out over here in the superheat region to P2, and I'd have state 2. So to use this, there needs to be a great enough pressure drop, and the quality cannot be too low. So with that, let's look up an example, and I'll show you how it works. So it's state 1. It's a mix, saturated mix at 400 kPa. State 2 is at 100 kPa, and T is 100 degrees C. And what I'm going to do is I can look this up in the tables. So I can look this up in the tables, and I will find that H2 is equal to 2675 kilojoules per Kelvin. So you have to do that. I had to do a lot of interpolation to get there. And then H1 is equal to 2675. It's equal to H sub F 604.3 plus X1 times H sub FG 2134.4. And these are at 400 kPa. And I solve and I get that X1 is equal to 0.97 or 97% quality. So I can do this. The tables in the back of the book have big jumps in numbers, so it's not as detailed. So it's a little bit harder. A lot of interpolation is needed to do it, but you can do it. And so it introduces a throttling calorimeter, which sometimes are talked about on PE exams or something like that, so I wanted you to be aware of it.